Good evening. We had looked at three-phase induction motor starting methods in the last class. Just to recapture, I would say that we had looked at for a squirrel cage induction motor, direct online starting, like directly switching on the three-phase supply and what kind of performance the induction motor is offering that we had looked at. And we use that as the reference for rest of the starting methods like star, delta, starting. Assuming that the stator winding is normally connected in delta, if we connect it in star, we said that the torque as well as that is the starting torque as well as starting current. Both are going to be reduced to 1/3 of DOL values, direct online starting values. This is what we said. The next method we looked at was auto transformer based starting. And if we have a turns ratio for the auto transformer as n:1, which is actually line side to the motor side. In that case, we are going to see that both starting current as well as the torque, that is starting current on the line side, as well as the torque, those are going to be reduced to 1 divided by n square as compared to DOL values. That's what we said in the third method. Then the fourth method we looked at was part winding starting, where the stator might have multiple windings or windings in multiple parts. So due to which, if you use only one part, the impedance will be Z. If you use two parts, it will be Z by 2. If you use three parts, then it will become Z divided by 3. So because of which, you are going to have Z being larger value, you are going to have lesser current during starting and lesser torque as well. So part winding starting will also reduce the current as well as torque, depending upon how many parts of the winding are available and how many you are using or you are putting them into service during starting. Then the fifth method that we talked about was impedance starting, where we can have a variable impedance connected in series with the induction motor winding. So we will have part of the voltage, part of the applied voltage is dropped in the external impedance. So we will apply only part of the voltage in to the induction motor, due to which the current is going to be limited and we are also going to have less amount of torque. Similar to this, we may be able to use an AC voltage controller, three-phase AC voltage controller, which is generally known as soft start. So in this particular case, we will start with a higher firing angle, alpha, and that will actually apply lower voltage. And as the speed picks up, we will be applying a larger amount of voltage by reducing the firing angle. So we are going to apply a larger voltage. So as the speed picks up, by reducing alpha, a larger voltage will be applied. So this is the next method of starting we talked about. And the last one, the final one, which we talked about was for wound rotor induction motor, where we would be able to reduce the starting current and improve the starting torque by rotor resistance control. So include external rotor resistance. So that is going to improve the starting performance considerably. So these are the different methods of starting that we looked at. Now what we are going to do is to work out one problem on our numerical example on the starting of induction motor. So the problem statement is somewhat like this. So let me try to show the problem statement here. So the problem is problem number 3, what we had looked at. So this is a 3-phase delta connected cage induction motor. It takes 2.67 times full load current and generates 0.8 times full load torque while being started by star delta starter. So let me first of all write that clearly. So what it says is star delta starting is being employed. So when that is employed, we already said in the previous slide, saying that if we are going to use star delta starting, then the starting current as well as starting torque will be 1/3 of the DOL value. So here what is given is the starting torque, the starting current is 2.67 times I full load or I rated. And similarly, the starting torque during the star delta starting method, the starting torque happens to be 0.8 times T full load. This is what is given as the data. Now what is being asked is what will be the normal DOL current and torque as a ratio of full load values. So the first and foremost thing is when we employ star delta starting, we said 1/3 of I DOL will be I star delta starting current. Similarly, 1/3 of T DOL will be the electromagnetic torque developed during star delta. So this is what we said in the last class. So correspondingly, we should be able to say I DOL is going to be equal to 3 times I star delta. And I star delta is given as 2.67. So this should be 3 times 2.67 times I full load. So this is approximately 8 times. 2.6667 multiplied by 3 will be 8. So 8 times I full load will be I DOL. Similarly, the torque corresponding to DOL direct online starting will be 3 times that is whatever is the torque during star delta starting. So that is going to be 3 times 0.8 times T full load. So that is going to be 2.4 times T full load. The full load torque as compared to that, this is going to be 2.4 times when I employ star delta starting for this particular induction machine. Okay. So another thing that is being asked is what is the full load slip of the motor? So let us first of all try to calculate that. So the full load slip of the motor we can calculate by making use of this expression that if I talk about TE full load, we had written this as 3 I2 dash square R2 dash divided by S omega S. This is what is TE full load. Whereas if you talk about TE starting, we should write this as 3 I2 starting dash square R2 dash divided by slip during starting is 1. So I have to simply use omega S. So when I take the ratio of this TE full load and TE starting, I should be able to write this as TE starting divided by TE full load is equal to 3 and 3 will get cancelled. So I should be able to write this as I2 starting divided by I2 full load, maybe dash, I can put for both whole square, multiplied by omega s, and omega s will get cancelled. R2 dash and R2 dash will also get cancelled. So only thing what I have is, if I call this as full load slip, I should multiply this by full load slip. That's all. So this is the ratio of starting torque to full load torque. So using this expression, I should be able to write TEDOL is going to be a 2.4 times T full load. So I should say this is 2. T starting divided by TE full load. That is going to be 2.4, which is equal to IDOL. So I can write I2 starting as IDOL divided by I full load, the whole square, multiplied by S full load. Okay, so I should be able to write this as the torque is 2.4 times, whereas the current is 8 times. So I should be able to write this as 2.4 equal to 8 square multiplied by S full load. So from which I should write S full load is equal to slip at full load condition is 2.4 divided by 64. So this is going to be the full load slip value. We can calculate this as the full load slip value, which comes out to be 0.0375. Okay. Now, the next one that is being asked. The next one that is being asked is, let me just look at the word file. So it says, calculate the tapping of the variac. Variac means auto transformer. So calculate the tapping of the auto transformer and the corresponding value of starting torque if the starting current is to be limited to twice the full load value while employing auto transformer starting. So the current has to be limited to twice the full load value. That's what is being told. So the current has to be limited to twice the full load value. So let us say this is subdivision number 3. In auto transformer starting, we want current to be limited to 2 times I full load. So normal direct online starting current is 8 times I full load, but that has to be limited to 2 times I full load. So I can write I auto transformer starting divided by I DOL starting will be equal to 2 times I full load divided by 8 times I full load. So it is going to reduce it to 1/4 of the original value. And we said that auto transformer starting is going to limit the current to 1 by n square times. If the turns ratio is in such a manner that n is to 1 is equal to line side to motor side. This is what we said. So which means very clearly in this particular case, we should have the turns ratio to be 2:1. This is going to be the turns ratio of the variac or auto transformer that we need to use. And if we have to calculate what is the corresponding starting torque when I'm using the auto transformer starting. So this will be again whatever is the torque during DOL condition divided by 4, because both current as well as torque will be reduced by a factor of 1 by n square. So T DOL said 2.4. So this should be 2.4 divided by 4 times TE full load. So that means we are going to have only 60% of the full load torque as the starting torque if we are using an auto transformer with the turns ratio which is corresponding to 2:1. That is, 2 turns are on the line side and 1 turn is going to be on the motor side. Now the last subdivision what is being asked is if the rotor cage alone has to be redesigned to limit the direct online starting current to 4 times the full load value, what should be the percentage increase in the resistance of the cage, assuming that stator impedances and rotor reactance are neglected? So what is being asked is, if we assume that we are giving the rotor current to be I2 dash or I1, that is going to be simply V1 divided by R2 dash. That's it. We are neglecting R1, X1, and X2. All of them are neglected. So V1 by R2 dash is going to be the current that is drawn by the motor. So during starting, we are going to have V1 divided by R2 dash is going to be 8 times I full load. That is what we had calculated as I DOL, right? That's what we had calculated as I DOL. I DOL was 8 times I full load. Now, what we want to reduce by increasing R2 dash, we want to reduce the current to the starting current to 4 times IFL. That is 4 times full load current, which means the current needs to be halved. So the current needs to be halved as compared to IDOL. So whatever was the original IDOL, compared to that, it needs to be halved. That means we have to have V1 divided by R2 dash new. That has to be equal to 4 times I full load. So if I compare equation 1 and equation 2, I should be able to say that R2 dash new has to be 2 times R2 dash. So that means we have to double the rotor resistance or the increase in the rotor resistance. Increase in the rotor resistance will be actually 200% or 100% increase. So totally, if you look at it, 100% plus 100%, it will become 200%. So the increase in the rotor resistance has to be quite high, so it has to be doubled. That's what it means. And if we have to calculate the corresponding torque value, what is the kind of torque value we are going to have? So if the torque is proportional to I square, so if the current is halved, then we are going to have the torque becoming 1/4. The torque will be becoming 1/4. So again, we are going to see that the original DOL torque, what we saw was 2.4 times T full load. So compared to that, we'll have to have 1/4. So we should say 2.4 times TE full load divided by 4 will be the new TE starting value. So that is going to be 0.6 times TE full. Okay. So this has employed essentially 3 different types of starting methods. One was star delta starting. The other one was the auto transformer starting. The third one that was employed was rotor resistance. In a way, the rotor resistance has been varied by redesigning the rotor itself. So all of them have been compared with direct online starting condition. Okay. So this is how the starting of the induction motor can be done. And the starting performance, at least the current can be reduced considerably. So that's what we were looking. Okay. Now let us migrate to the speed control of a 3-phase induction. So the speed control of a 3-phase induction motor, if you look at, because the synchronous speed is 120 F by P RPM. So, and the rotor speed is very close to the synchronous speed. So if I want to change the speed, one of them is by changing the frequency. Another one is probably by changing the pole. But the torque can be controlled definitely, because we said the torque is 3V1 square divided by R1 plus R2 dash divided by S, the whole square, plus X1 plus X2 dash, the whole square. And in the numerator, I have to have R2 dash divided by S, synchronous speed, omega S. So this is what is torque. So the torque can also be controlled probably by changing the voltage to some extent. I cannot say it can be changed to a large extent. Speed, it is very, very difficult to change it by changing the voltage. So generally, the best method of speed control would be either by changing the frequency or by changing the pole, the number of poles. So the another easier method of speed control that can be employed in wound rotor induction motor. So in a wound rotor induction motor, if you may recall, we said in any induction motor for that matter, the rotor input power is to the rotor copper losses with respect to the rotor output power, that is the mechanical output power. This is generally attributed to the ratio in the form of 1 is to S is to 1 minus S. So if I want to change the speed, that means the slip is going to be changed. So for changing the slip, I should be able to change, I can change the slip by changing the rotor copper losses. So if I am changing the rotor copper loss, that can be done because this is I2 square R2, whereas this is going to be I2 square R2 divided by S, and this is going to be I2 square R2 divided by S multiplied by 1 minus S. So by adjusting the slip, I should be able to adjust what is the fraction of the copper losses that take place or that is incurred by the rotor circuit. So I should be able to adjust how much is the output that is coming out of the rotor in the form of mechanical output. So if R2 dash by S is kept as a constant, which is actually going to make the rotor input power as a constant. So let me, rather than saying just R2 dash by S, if I am trying to keep I2 square R2 dash by S is kept as a constant, in that case, by varying R2 dash divided by R2 dash in proportion to the slip. So if I increase R2 dash, correspondingly slip will increase. So if I change R2 dash, then correspondingly slip is going to increase, which means the speed will vary. So if the slip increases, speed will actually, if slip is increasing because of increasing the rotor resistance, then we are going to have speed decrease. So this is one of the easiest methods of, achieving speed control, especially in the case of a wound rotor induction motor. So in the wound rotor induction motor, we have the luxury of changing the rotor resistance, and by changing the rotor resistance, we would see that for a given rotor input power, the slip automatically will change. So if I increase the rotor resistance, the slip will increase. If the slip is increasing, then we are going to have the speed decreasing automatically. So what this can be, implying is, if let us say this is the normal speed torque characteristics of the induction motor. This is going to be the speed torque characteristics of the induction motor. And we said that we are going to have the Tmax. This is the Tmax value. This is the Te, and this is the speed of the induction motor. So when Tmax is occurring for the induction motor, the maximum torque is occurring for the induction motor. At that point, the slip is going to be R2 divided by X2. This is what is going to be the slip value. So if I am increasing R2 further and further, we are going to have this, this particular slip value, the slip at maximum torque occurring at larger and larger values of slip. So I'm going to have, if I increase the rotor resistance, I will have the characteristics somewhat like this. I'm going to have multiple characteristics like this. So this is going to be one of the slip values. This is going to be the other slip value. So these are with higher values of rotor resistance. So this is with higher R2. So whenever R2 is going to increase further and further, we are going to have more and more droop in the slip torque characteristics, which means if I am looking at a particular torque value, let us say this is the load torque demand, which is a constant value. For R2, 1, I am going to have a particular speed. But for R2, 2 rotor resistance, I'm going to have a little reduced speed. And for R2, 3 rotor resistance, I will have further reduced speed. So I'm going to have different values of speed being achieved when I am trying to vary the rotor resistance in a wound rotor induction motor. So in a wound rotor induction motor, rotor resistance control is a legitimate method of speed control. This can allow you to achieve a good amount of speed control at a given torque value. However, this is going to be a lossy method because I2 square R2, this is going to be the rotor copper loss. So if R2 increases, then rotor copper loss or power dissipated in rotor resistance, that will also increase. So that means the efficiency is going to decrease. So the efficiency will decrease. So this is definitely not an efficient method of speed control. But however, this is one of the simpler methods of speed control. If you don't mind, losing some amount of power, this is one of the easiest methods of speed control. So what we are going to see is, if this is the three-phase supply, which is actually being fed to the stator circuit, and this is our rotor circuit here, and we are having the rotor winding, which is actually seen in wound rotor induction motor. So from the rotor circuit, we are going to have variable resistance connected like this before the rotor slip rings, the rotor terminals are short circuited. So this is going to be a variable resistance what we see. So this is going to be R2 dash external. What we are connecting is actually R2 external. So the rotor resistance, additional rotor resistance is connected externally. And here we are going to provide a three-phase 50 Hertz supply, which is from the grid on the stator side. So this is going to be the stator supply, whereas these are going to be the rotor terminals. So now if rather than using physical resistance, three-phase resistance directly, can we implement it in a simpler way? So if we look at it, we should be able to implement it somewhat like this. This particular method of implementation is called static rotor resistance control. So in static rotor resistance control, what we are going to do is the stator will be connected directly to a three-phase supply. So let me show this as the stator, and this is connected to the three-phase supply, which is three-phase 50 Hertz supply from the grid. So this is going to be from the power grid. So this is the stator supply. Now, as far as the rotor is concerned, the rotor is having the three-phase input somewhat like this. Now, this three-phase winding will be connected to a diode rectifier. So let me show a diode rectifier somewhat like this. And the AC which is coming out of the rotor, that is going to be a variable frequency AC, because that is going to be at a frequency of S times F1. If F1 is 50 Hertz, what is the frequency available is going to be S times 50 Hertz. That is going to be the frequency at the rotor circuit. Now, this will be connected to a diode rectifier, which will convert that rotor current, which is coming at a variable frequency, that will be converted into DC. So this diode will convert that into DC, and that is going to be passed through a resistance. So let me show the resistance connected somewhat like this. So this is the resistance that is connected continuously. Okay. So we are going to have an inductance here. So the inductance, and this is the kind of current that is flowing here. Now, if I vary this rotor resistance with the help of a switch, which is connected right across this is a solid state switch. So let me show this as an IGBT. And let's say this is some S1. And this is the DC link resistance RD. And this is going to be LD, which is the inductance that is connected to smoothen the current somewhat. So this is the filter inductance. This is the resistance on the DC link, and this is going to be the switch S1. Now, if S1 is on, whatever is the resistance seen by the diode rectifier, so external resistance, what is connected, that is going to be 0. Whereas if S1 is off, Then we are going to have the R2 external, what is seen by the diode rectifier, that is going to be equal to RD itself. So I can say the equivalent resistance visualized by or seen by the diode rectifier, that is going to be equal to RD multiplied by whatever is the off interval plus 0 multiplied by on interval divided by T on plus T off. Because if I assume that the switch is going to be turned on and turned off at a very, very high frequency with a duty ratio D, where D is going to be T on divided by T on plus T off. And T on plus T off is going to be 1 in this particular case, and D is a fraction of that. So I should be able to write this particular expression as RD multiplied by 1 minus D, where this D is the duty ratio of this particular switch. So the duty ratio of this particular switch is going to be D. So RD multiplied by 1 minus D will be the overall resistance visualized by this particular diode rectifier. So you can say in this particular case, the total copper loss incurred in the rotor circuit of the induction motor. So that is going to be 3I2 square R2, whatever is the inherent resistance of the rotor circuit, rotor winding. And apart from that, we are also incur some loss in this resistance, which will be ID square RD multiplied by 1 minus T. So this is going to be the total loss incurred in the rotor circuit. Now this entire thing will correspond to S times whatever is the rotor input. If the rotor input is assumed to be a constant, then very clearly this, according to whatever is the duty ratio, this particular copper loss is going to change, because of which S will also change, or the speed of the induction motor will change. Now, it's not going to be easy to calculate this in a straightforward manner. If we want to use the equivalent circuit kind of calculation, then we should be able to see how this RD multiplied by 1 minus D multiplied by ID square can be represented in the equivalent circuit itself. So, if we say the copper loss incurred in the external rotor resistance, that is equal to ID square RD multiplied by 1 minus T. This is going to be the copper loss incurred in the external rotor resistance. Okay. Now what we need to do is, if I am representing the induction motor in the form of a per phase equivalent circuit, I would say V1 is the input voltage per phase on the stator side, and R1 and X1 are the stator resistance, stator winding resistance and leakage reactance respectively. Now, I will have definitely X2 dash, which is the rotor resistance as well, and R2 dash divided by S, which is the inherent rotor resistance visualized from the stator side, and the mechanical power input is also now incorporated into this. Now, I would like to represent this IRD also, if it is possible, with the help of an external resistance. So let us say R external per phase. I want to represent this as R external dash per phase. And that has to be divided by S as well as per the equivalent circuit. Now what I want to calculate is what is this per phase equivalent resistance value? How will I get the equivalent resistance value from the original value of RD? That's what I want to know now. So this is the total copper loss incurred in the external rotor resistance, and this is corresponding to all the three phases. So this is corresponding to all the three phases of the induction motor, which has to be ultimately represented in the per phase format in this particular way. So if ID square RD multiplied by 1 minus D corresponds to the three-phase copper loss, I should be able to write this as some 3 multiplied by I2 square multiplied by R2. Rather than writing this as R2, I should write R external, right? So this is what will give me what is the value of R external. Now, because this is a diode rectifier and this inductance, filter inductance is a large value, we had already derived this, if you may recall, on the AC side. If I try to look at the current, I am going to have this current only for 120 degrees in the positive half cycle and 120 degrees in the negative half cycle for each of the phases. So if I try to look at this as IRA and this as IRB and this as IRC, IRA will look like this. So this will be something like only 120 degrees. And this is going to be the midpoint, which is corresponding to pi or 180 degrees. And again, this will correspond to 120 degrees. So out of total 180 degrees, the conduction is going to take place during the positive half cycle only for 120 degrees. Similarly, during the negative half cycle also, it is going to take place only for 120 degrees. So if I try to calculate the RMS value, so IRA for RMS, if I try to calculate, we wrote this as square root of 120 divided by 180 multiplied by whatever is the DC value, because here the current we are assuming it is ripple free. So if I try to look at the DC current, the DC side current, it will be literally somewhat like this. So this is omega T. And if I try to look at the DC current, it is going to be some fixed value which is corresponding to ID. Now this will also be ID and this will be minus ID. So the RMS value will be 120 divided by 180 square root of that multiplied by ID. That's why we wrote this as root of 2 by 3 times ID. So this is what we wrote as the per phase RMS current. Now this is the per phase RMS current we are talking about, which is also incidentally the rotor winding current. So I should be able to write here, if this is the per phase current, I should be able to write this as 3 multiplied by root of 2 by 3 multiplied by ID, the whole square multiplied by R external. So this is going to be this will come out to be this 3 and this 3 will get cancelled, and we are going to have 2 times ID square R external is going to be ID square multiplied by RD multiplied by 1 minus D. So this I'm just reproducing here, and this is equal to 2 times ID square R external. So from which I should be able to say R external as visualized from the per phase rotor equivalent, that will be equal to RD multiplied by 1 minus D divided by 2. So this R external dash will be simply RD dash divided by 2 multiplied by 1 minus T. So I should be able to draw the equivalent circuit somewhat like this. So instead of writing here R external dash, I should be able to write this as RD dash multiplied by 1 minus T divided by 2S. Because the rotor resistance has to be divided by the slip if I want to transfer it over to the stator side itself. Because the rotor current will be at slip frequency, but the stator side current will be at 50 Hertz. So everything needs to be converted to 50 Hertz. So we are going to have basically the rotor copper loss in static rotor resistance control scheme. So the total rotor copper loss in static rotor resistance control scheme will be equal to I2 dash square R2 dash plus RD dash multiplied by 1 minus T. So this is going to be the per phase loss. So this has to be multiplied by 3. So this is going to be essentially the total amount of loss that is incurred by all the 3 phases of the rotor circuit plus external resistance. So that is going to be 3I2 dash square multiplied by R2 dash plus RD dash divided by 2 multiplied by 1 minus T. So in this particular case, we should be able to calculate the output power. What is coming out of the induction motor will be 3I2 dash square 1 minus S divided by S multiplied by R2 dash plus RD dash divided by 2 multiplied by 1 minus D. So by changing the duty ratio, we will be in a position to control the speed of the induction motor at a given torque, and we will be able to adjust the rotor copper losses, the fraction of rotor copper losses and the rotor output. So when I look at the overall characteristics of the induction motor, okay, so let us say originally this has been the synchronous speed, and what we are showing here is the speed, and this axis is representing the torque. And I'm going to draw only the uh, uh, portion where the torque is proportional to slip. So this is the natural characteristics of the induction motor. As I increase the rotor resistance, I'm going to have the characteristics getting modified like this. This is the way the characteristics are going to get modified. So this is the direction in which the rotor resistance is increasing. And the rotor resistance will increase when the duty ratio is decreasing. So here duty ratio is decreasing in this direction. So duty ratio is going to decrease in this direction. So if I am looking at a particular value of load torque being delivered, so we would be able to obtain either this particular speed at a particular duty ratio. Maybe the duty ratio is 1, and maybe the duty ratio is reduced to 0.9. Then you are going to have a speed like this. When it is reduced to 0.7 or 0.6, we are going to have the speed correspondingly decreasing. As the duty ratio decreases, the speed will also decrease. So as the duty ratio decreases, the speed will decrease even if TE delivered is the same. So this is the way the rotor resistance control, static rotor resistance control is going to work. So if we are looking at the overall control scheme, how it is designed. So let us say control scheme for static rotor resistance control. So what we are looking at is to achieve a particular value of speed. So we are going to say that we want to achieve a particular value of reference speed. And what is the actual speed that is fed back here? So this is going to be the actual speed of the rotor. Now, what comes here is speed error. So this is going to be the speed error. Now, this speed error will be passed through a speed controller. The speed controller is going to decide what is the kind of torque or current that we require from the rotor circuit. So this is going to decide probably the torque. Let us say we are getting a reference torque. Now this will have, first of all, the load torque being subtracted. Okay. So whatever is the actual torque, either we sense that, or another way to do it is instead of torque reference, we can say this is the current reference. So this is going to be what is the current reference that we are getting from the speed controller. Now, what we are going to do is from the current reference, we will compare that with actual current. So this is going to be I actual that is going to be compared, and this is going to be passed through um, a current controller. So we are going to have a current controller here. Now the current controller is going to decide what is going to be the duty ratio. So this will adjust the duty ratio of the switch that is being used along with the static rotor resistance control. So this is going to adjust the duty ratio. Now, let us try to draw rest of the scheme of the induction motor. So let us say this is the induction motor here. And to this, the three-phase supply is given here. So this is the three-phase supply. And here is the rotor circuit. And we are going to have the three-phase winding in the rotor circuit. And that is going to be connected, let us say, to a diode rectifier. So here is the diode rectifier. So these three phases are connected to the diode rectifier here. And we are going to have an inductor, and we have a resistance, and we are going to have the switch here. So this is the switch. Now the duty ratio control is going to directly feed the duty ratio to the switch. And let me complete this circuit. This is going to go here, whereas this is going to be connected here. And we have to connect this as well here. Okay. Now we can sense what is the current here. So let me probably sense the current here. So this is the current that is being sensed here. This is the current that is being sensed here. And this duty ratio control is going to the switch here. This is the switch. Now, from here, the I actual is going to be fed to this particular node. So this is the I actual that is being fed so that the current controller is going in a position to process the error. The same way from this motor, we have to have some kind of speed sensing mechanism. So speed sensor. So this will be mechanical to electrical quantity conversion. The speed transducer will convert that into the electrical quantity. Now this actual speed comes out of here and that will be fed to the actual speed here. So this is the way generally the rotor resistance control scheme is going to be designed, and all we need is only one current sensor, and even the speed can be sometimes computed, so we don't even have to have the speed sensor here. Speed can be computed based on maybe the applied current and the frequency and so on. Okay. So the rotor resistance control scheme can be implemented simply by connecting a diode rectifier and an external switch and an external resistance. The external switch's duty ratio is being controlled here to obtain various speeds. The major two drawbacks of this scheme are this can be used only for wound rotor induction motor. It cannot be used in squirrel cage induction motor. This can be used only in wound rotor induction motor or slip ring induction motor. This is one of the major problems. The second problem is this scheme is very lossy. So efficiency is poor. So rather than wasting the energy in the external resistance, can we feed that back to the mains or the induction motor itself? Can we take whatever is I2 square R2, 3 times I2 square R2? We said that the rotor copper losses are generally S times the rotor input. So the rotor input power, when I multiply it by slip, we get the rotor copper losses. So rather than wasting the power in rotor resistance, can we really, return this power to the grid or retrieve this power in some way? So this particular power we call as generally slip power. Because it is slip times the rotor input, we call this entire thing as slip power. So can we recover the slip power? So a scheme which is recovering the slip power is generally known as slip power recovery scheme. So slip power recovery scheme actually takes up the energy available in the rotor terminal and it tries to feed it back to the mains. So if that can be done, the efficiency of the drive scheme can be improved tremendously. So we will look at slip power recovery scheme in the next class, and this can also be employed only for wound rotor induction.